Hello, I'm Bernie Ziegler, and I'm going to tell you about the new Markov Modeling facility within the MS4 Me modeling environment. Just a brief overview, and we'll follow with other videos to tell you more in detail. The MS4 Me facility for Markov modeling helps you quickly and confidently develop simulation models of systems and their components. Easily include both deterministic and probabilistic behaviors within the components and their interaction. Study the resulting system behavior with Monte Carlo simulation, immediately available with the push of a button. And you can quickly create fast-running analytic simplifications of systems and their component models, and employ the results of these simplified models to analyze and narrow down the parameter space of the original simulation models. The toolset for Markov modeling in MS4 Me offers an easy-to-use set of tools to develop Markov models as full-fledged DEVS models, able to be integrated with other DEVS models. And it makes it much easier to develop probabilistic and stochastic DEVS models. It automates a lot of the development tasks that otherwise you'd have to do manually. This raises the power of model development to a new level of speed and confidence, which is unparalleled in other commercial and academic tools on the market. You will be able to develop families of DEVS models for cutting-edge, challenging areas such as system of systems, agent-directed systems and agent-based models, and DEVS-based development of the web, the cloud, and Internet of Things. The new Markov model classes extend the existing FDDEVs, finite deterministic DEVs, and FPDEVs, the finite probabilistic DEVs, to include finite state continuous time Markov models, CTMs, discrete time Markov chain models, DTM, and the Markov matrix Markov mate classes. CTM models represent complex systems at the level of individual actors. Multiple actors can be represented as CTMs, with individual states and transitions, inputs and outputs, which extends the usual Markov modeling capability and allows these individual actors to interact with other atomic models within coupled models using DEVS coupling in the usual way. Now we'll talk about two or three examples. Stock market is one. It's a simple example from Wikipedia, which can be created and solved in minutes using the new facility. It has three states: the bull market, increasing stock value; bear market, decreasing stock value; and a stagnant market, neither increasing nor decreasing. Transition probabilities between states represent the likelihood of changing from one form of behavior to another. Here are the states, and these are the probabilities of transitioning between states. The resulting model predicts the probability of being in each state, that is, the relative time spent in each form of behavior over a long time span. For example, if you started in the bull state, the model predicts how long you stay in that state before transitioning to another state, such as the bear state. You stay in that state for some time before transitioning to the stagnant state or some other state, and so on, over a period of time. The relative amount of time you spend in each state is predicted by the model as the probability of occupying that state. You create this model with very simple clicks on the state and the arrow buttons, and you assign probabilities as you would to create any model. One example where Markov modeling is very fundamentally used is that of reliability and vulnerability modeling. Here the systems can be abstracted into healthy, failed, and repaired states. And transition from healthy to failed is represented by the failure rate. Equipped with output to report failure and input to transition back to healthy, the model can be coupled to repair and other system components and simulated as CTMs. The output and input allow these Markov models to interact with other components, for example, to be repaired in this case. The repair input, however, can be replaced by a rate of repair and studied using the conversion to a Markov matrix model. This is done by a simple click of the button, and the Markov approximation is created. The reliability design, such as redundant systems, can be simulated and analyzed in this way. For example, the effect of using units in parallel for redundancy or adding additional repair to this redundancy can be studied, and the advantage of doing so can be traded off against the cost of these extra additions. Vulnerability of systems can be modeled in the same way. A major use of Markov modeling is in the healthcare domain, where the evaluation of cost effectiveness of health interventions can be done, and has a long tradition of being applied. It's extensively used in evaluating the trade-off of quality of life with cost in drug therapy, for example. Cohort models, which follow patients as a group over time in aggregated form, are easier to develop and calibrate. They run very fast, but they cannot accommodate patient differences. Individual models can accommodate individual patients' stochastic disease and treatment trajectories, but they require much more detailed data, are much slower to execute, and require numerous runs to achieve statistical validity. The new MS4 Me Markov modeling facility allows both approaches to be used in an integrated manner. Markov matrix supports cohort-level models where aggregations of homogeneous patients are tracked. Embedding CTM models within multi-aspects in the system entity structure enables them to serve within patient models to produce individualized stochastic and disease trajectories. For example, a simple model in which we have 4 states, healthy, sick, very sick, and dead, can be represented using the CTM facility and studied with individuals transitioning through these states with different values for the probabilities. The potency or effectiveness of treatment is the probability of transitioning from very sick to sick. The overall metrics for performance of such models are of this form. The quality of health is the probability of being in the healthy state over the probability of being in the sick state plus the probability of being in the very sick state. So the more that you occupy the healthy state, the higher the quality of health. The cost of treatment varies with the probability of being very sick and the potency or effectiveness of treatment, so that the longer you stay in the very sick state, the more it costs before you can transition back to the sick state. When you have alternate treatments, which would have different potencies of treatment, the value of treatment is comparable in each as the quality of health over the cost of treatment. If we drop the dead state as very unlikely, we get an approximation which is easily represented with the Markov matrix and is performed with the press of a button, and that gives a very fast approximation which can be very good for the overall cohort population of patients. For more information, go to the MS4 Systems website or send email to support@ms4systems.com. Please look out for more videos on how to use the new Markov Modeling facility in MS4 Me and further information on the domains to which it applies.